Spend a few more minutes talking about the strings, because I know that the string vibrations and the vibrations in the pipes tend to give people some trouble. So if you have any questions, I'll be happy to discuss them. And after that, there's a whole lot to do, so we've got to move on. So there is always a compromise as to how much you can do. Now, a couple of easy things. Oftentimes you are asked, for example, to find out the normal modes or the modes of vibration in a string, let's say, or in a pipe. So a pipe would be the nuts and bolts of a wind organ, wind-based organ. This could be the nuts and bolts of something like a guitar or the piano or what have you. The most interesting thing here, the most difficult thing probably is the pipe. So let me just briefly tell you what it is, because I went through this last time and it's difficult to give a problem on this without having to draw a lot. So let's say you have a pipe like this which is closed at one end, right? So this is closed at one end. So if you have sound that's going through, circulating through here, let's say the best it can do is it has to turn around at this end, right? Because this end is a complete block. And it can vibrate as much as it wants at the other end. So if you were to look at the amplitude of vibration, then at the lowest, okay, so in other words, you will have a node meaning a point of no vibration, right? And since this end is open, for the stable vibration to happen of the air column, this would be an anti-node, which would be an area where you can have the maximum vibration. So now it becomes a very simple problem of figuring out what kind of vibrations you can have of the air mass here. Clearly there won't be much vibration here, there can be a lot of vibration here. So therefore if you draw how this wave is, you will find there is more vibration here and less vibration here, and we would typically denote that the lowest mode by a wave where this would be the wavelength. So if this is L, right, and if you think of a wavelength lambda as this whole length, then this distance here would be lambda over 2, and this distance here would be lambda over 4. So therefore this would be lambda over 4, and since you can't make anything simpler than this is the lowest mode, okay? So lambda over 4 here is L. So lambda is 4L. And since we know that the speed of a wave, let's say v, is the distance traveled by the wave, that would be, let's say, lambda distance, over a period of time, that would be t, the actual period of the wave in which it goes through one full oscillation, we write this as lambda f. So therefore if you're looking for the frequency would clearly be the speed of the wave divided by the wavelength lambda. So now you can see that the frequency here that you will get would be the speed of the wave divided by lambda, but lambda in this case is 4L. So that would be your frequency. Okay? So it's very simple. The next one that you would consider, the next higher one, so that's the lowest frequency you can have, and the denominator is V over 4L. So this is something we did last time, so I'm just repeating just so that you guys feel confident about how to do these. Let's again take a one-end closed situation. And now you can have also a situation like this, right? You can have a situation, but that would be a somewhat higher frequency. So this would be lambda over 2, this would be half lambda, so this is L again. So L would be 3 over 2 times lambda. So therefore, if I go by the argument I made before, lambda would now be 2/3 L, right, instead of 4L. And hence the frequency by the argument I made before, which is V over F, frequency is V over lambda. So this would be V over lambda is 2/3 L, right? So that would be 3V over 2L. And this frequency would clearly be higher because the denominator 2/3 is 0.66 and there the denominator is 4. So you can clearly see that there is a big difference between the frequencies that your ears will hear between the first case and the second. Any questions on this? Yes. Yeah.
Over 4 and not over 2.
Because if you look at the picture of the wavelength, the whole wavelength drawn is lambda, right? So half of it is lambda over 2, and then I didn't put in arrows. Maybe that will help you. So this is here, right? And this is here. But this thing is only up to here. Okay? Very important that you don't mess up. Yeah. How would you know?
How would you know that the length there would be anti-node or it would be 3/2?
Okay, that's a very good question. That's a stable vibration. So that's a vibration that will sound good to your ear and you'll be able to make out. Okay? It will not be not be like me trying to play the saxophone, which would sound very bad. That would be an unstable mode and that wouldn't look like this.
But what information would help us to deduce that in the question?
You don't have any information to deduce that in the question. That is the stable sound that you can hear. So in all these things, for you to be able to hear a stable sound frequency, a single frequency in particular, it will have to have this form of vibration. That doesn't mean that the total vibration that's going on is just this. It means that this is there embedded among maybe 55 other vibrations that are going on at the same time as you are playing something. Now, there is another interesting point. You know that sound speed in air is about 300 some meters per second, right? So that's 1/3 of a kilometer per second. And most of these organs are going to be relatively small compared to a kilometer, right? So therefore these patterns form instantaneously. So they literally form in less than milliseconds probably. I haven't done the calculation, but so our brain responds at about some tens of milliseconds typically. So you won't even know, or you won't even be able to analyze the time scale in which this forms. Okay. Any other questions? Okay. So this would be the case for a half closed pipe. Now, if you have a fully closed pipe, again something we did last time, right? Then of course you have to have an antinode here and there, which means the lowest frequency you can have would be half a wavelength. So here L would be lambda over 2. And you can do the remainder of the calculation. The frequency is V over lambda, so V over 2L. You can have the next highest frequency here would be, let's see, we have this, we have to have a node here, so we can do this, right? So this would be L equal to lambda, and this would give you the next higher frequency, okay? So this is how you work these. It's a matter of just drawing it correctly and then being able to relate L with lambda. And once you know that V is lambda f, which is what I have shown here. One more time. V is lambda. This is the easiest way to remember it. Distance traveled over time taken, lambda over t, which is lambda. So once you know this, the rest of it is trivial. Suppose I have an open pipe. You have open pipes, for example, in many cases. Now, here, of course, you'll have an antinode here and an antinode there, meaning maximum vibrations at both the ends. So the lowest thing you can have would be a frequency like this, would be a standing wave pattern like this. So this is, okay, so let's be very clear. So distance from here to here is lambda, right? One more time. So here to here, this is even less. Here to here is lambda over 4, and just from here to here is going to be lambda over 2. So once you have figured out that here L is equal to lambda over 2, you can do your calculations for the open pipe. So that's all you do. These problems are actually tremendously simple. Yeah. Huh? Why? Is it half? Oh yeah, you're right. Half plus 1/3. This is half plus 1/4. Yeah, you're right. 3 over 4. I'm sorry. 3 over 4. So this is 4 over 3. 4 over 3. Thanks. 4 over 3. Yeah. So anyway, I'm not going to belabor this, but this is how you do it. Yeah.
Is it like half and then quarter, like the one on the
For the open one?
No. Yeah, for the open one, the diagram is
Oh yeah. This is 2. This is what happens when you don't eat breakfast. This is 4. Okay. All right. Any other questions? Yes. Huh? Yeah, stable pattern at the open end will always be an antinode for a stable. Somebody had a raised hand. Okay. All right, good. So anyway, I just want to make sure that you guys feel comfortable because these are very simple things. The other thing that some of you were asking me questions yesterday is if you have a string like this. Let's say the string itself is massless, but the mass of the string is effectively replaced by putting in a mass here. Then the actual, so let's say the length of the string is L, then the speed of sound in this is actually the tension in the string divided by the mass per unit length square root. This is a formula I gave without derivation last time, and I'm repeating it again, because it's often very useful in looking at how quickly sound propagates from this point to that point. So tension, of course, will be here mg, and mu would be let's say the mass of mu will be mass per unit length. The total mass is here, length is here, so m over L. So you can calculate these things, and there is a worked out example of that in the lecture notes I have posted. Okay, I'm not going to go over it because I'm trying to keep an eye on time such that we don't get too bogged down with some of the things that you can do yourself. One of the things I want to cover, because that has a lot of practical application, but again I'll do it at a very simple intuitive level, is a Doppler effect. So when you, for example, make an ultrasonic image of your heart, let's say, you will see that there are colors that show up on the screen. There are red and blue and so on. That red color and the blue color is tied to Doppler effect. So similarly, any kind of ultrasound that you do that's tracking any kind of blood flow or fluid flow in the body, it is essentially tracking what's going on using Doppler effect. So what is Doppler effect? So at the simplest level, I'm sure you know that if a car is coming at you and honking, the frequency of the car will change, right? In fact, the frequency goes up as the car comes towards you, and as the car is receding, the frequency goes down. That's Doppler effect. So a very simple thing to see and understand. Suppose I have 2 points here, and this point is the source of the sound, and this point is the listener. So the source of the sound is emitting sound that is moving at speed v, is wavelength lambda that's associated with the sound being emitted, times the source frequency. I would call that Fs. So Fs is the frequency of the source. This is the Fs here. Frequency of sound at source. Now, if as a listener you are not moving, then you will be hearing the very same thing. Anyway, so I can write this as Fs as v over lambda. And if VL is 0, so the listener, as the listener you are not moving, then the frequency FL that you will hear would also be V, same V because you are not moving, over the same lambda, so this would be Fs. So this is the benchmark result. So if you are not moving, if the source is not moving, the frequency that you would hear would be the exact same of what the frequency is being emitted by the source, as long as you're hearing correctly, that is, which I assume is the case here. So now suppose, while the source is fixed, you go towards the source. Or alternatively, the source comes towards you. It doesn't matter. Even if the source comes towards you, you can assume the source is fixed and you are going towards the source, because it's relative motion after all. So, in other words, if VL, the speed of the listener is positive, let's say, then what happens is that the effective speed at which the source arrives at your ear goes up because you're going towards it. So the way you do it is requires a little bit of thinking at a distance rather than blindly trying to do relative velocity and so on. So if something is coming towards me, then the speed at which this thing is coming towards me obviously goes up, right? So in other words, now what you'll have is that the frequency that the listener will pick up would not only be from the velocity that was already there, but also be from the listener's velocity, because now both the velocities are conspiring together to give you the frequency that you hear, and this would now be the new frequency. And you see, this new frequency FL would be greater than Fs. So that is the explanation as to why, if the source is coming towards you or you are going towards the source, you basically hear a higher frequency, because the effective velocity at which the noise or the sound hits your ear is going up. So V plus V. And similarly, if it's going the other way, so if VL, let's say, is negative, then the frequency that you'll hear is V minus VL over lambda. And at the simplest level, this would be FL less than Fs. So you would be hearing a smaller frequency. By the way, this is all sound, right? But the way we study, for example, the cosmos, the universe, the galaxies, and so on, is essentially by seeing the same thing for light. So the universe, as we know, is expanding. So it's continuously expanding. Now you may be asking, Where is it going? How long is it going to expand? The answer is we don't know. As far as we know, from the point of the Big Bang, the universe has been steadily expanding. The expansion rate may be changing, but these are things that are not easy to find. How do we know that the universe is expanding? Well, we know that the universe is expanding for sure because the light waves that are arriving to our eyes, their wavelength is actually going up. In other words, whatever it is that sent us the light wave, let's say a long time ago, by the time that light reaches my eyes, the wavelength of it will be changing, will be going up, and hence it must be receding from me. So we know that the universe as such is expanding, and every galaxy and super galaxy and clusters, and they're all getting away from each other. So we will perhaps eventually die a very cold death when everybody would be so far away that we won't be able to see anything at all in the sky. But the universe is expanding, and the way we know this is by looking at the Doppler effect, but in that case Doppler effect for light as opposed to Doppler effect for sound. Any questions? Okay, so I'm not going to go any deeper into the Doppler effect. One can easily have a far deeper analysis of the Doppler effect. If you're interested, just look it up in the textbook. All of these textbooks do a pretty good job of introducing Doppler effects and taking you to the basics of it. Because we have so many things, I don't want to overburden you with stuff that I feel can probably wait a little for you to pick up on. I would now want to do something which is a totally new topic and move into fluids. So this is one of the important later chapters that we go through because fluids are very important for us. By fluids, we normally would mean liquids and gases. This definition, by the way, has evolved even in the last 30-40 years. For example, in many ways, something like dirt is also a fluid, and we don't really think of them in the same category as this simple fluid. So we should probably think of them as simple fluids. By the same token, mud is also a fluid, as is milk, and these are colloidal fluids which have particles that are suspended at least over a long period of time in the liquid. So we are not considering colloids or complex fluids like mud or dirt and so on and so forth, or dust for that matter. And so at any rate, let's take a fluid in a container and let's put a lid on top of it and let's fill it up with some fluid. Let's say water. Let's say the cross section here is A, and I apply some force here F. So therefore the pressure that I am applying to this fluid would be F over A. Okay? F over A. So F over A is measured, as you know already, from stress and strain, newtons and meters squared, or pascals. And since fluid is heavy, this number in pascals tends to be quite large. For example, megapascals, or 10 to the 6 pascals, so on and so forth. Okay? So there is a very interesting thing about fluids. I'll first turn gravity off. So let's say, assume there is no gravity, because the fluids are heavy enough that unless this body of water is pretty large, the effect of gravity is at best minimal. So it is not really important right now. The effect of gravity, by the way, does become important if you are diving underwater, because the weight of water builds up and effect of gravity can become important. But here, and this is just a container, even if it's quite big, effect of gravity is not important. I want to take you to Pascal's principle many Pascal's principles show up, so you got to know which is what. But Pascal's principle says something quite astounding. It says in the absence of gravity, pressure applied to a fluid, like here, I'm applying a pressure. Is transmitted undiminished, which is very interesting, quite non-intuitive perhaps, is transmitted undiminished, so no decay in its strength, to every point in the fluid, including at the walls of the container. So in other words, if the fluid is at rest, more or less, this thing is going to be carrying the same pressure that I'm giving on the top. If you measure the pressure at this point, the pressure is going to be P, at this point P, at this point P, smack in the middle P, and so on. And that's the property of the fluid, that the pressure is transmitted undiminished. And this is a property, by the way, that we use in our daily life. For example, when you take your car to the service station and they want to take a look at the bottom of your car, they would lift it, right? What are they doing? They're actually using the fact that hydrostatic pressure is transmitted instantaneously in the fluid and applying a small amount of force multiple times to generate a large force that will actually lift up the car. You won't be able to lift up the car, but with the help of fluids, you can, without really doing a tremendous amount of work. So, now there is something important about it that I need to tell you. Pressure is a scalar. It's not a vector. So it has no sense of direction. Pressure is the same everywhere. It has no direction associated with it. Force is a vector. Actually, area also is a vector. Although we don't learn about it in this course, but area is a vector. Why is area a vector? Well, area is a vector for the following simple reason. If you look at this bottle here, you can, suppose I mark up, I don't have a marker here, but suppose I mark up just a square somewhere here. If you look at this square here would be sitting on a surface with a curvature. And the way area vector would be defined is the outward normal, outward perpendicular to that tiny bit of surface. That's how area vector is defined. So if it were concave, this is kind of concave here. Here the area vector would be the other way. So anyway, that's how it's defined. It transforms as a vector. It's a little bit mathematical, so I wouldn't get into that. But it suffices you to know that pressure is a scalar, not because of some strange magic, but it's a division or a multiplication, hence by two vectors. Yes?
Shut the container to no gravity instance would still have.
That's a very good question. So speed of propagation of any kind of disturbance in the water would be same as the speed of sound. It's the sound that will carry the disturbance from one point to the other. And since sound travels pretty fast, the answer is it would quickly, the moment it pretty much settles down, it will acquire the same pressure. But as long as it's flowing, it won't. As long as it's flowing, it won't. And I'll tell you why. In fact, I was going to come to this point. So you see, the pressure is the same, but what about the force? it turns out that this is not moving, right? The fluid is at rest. Now if the fluid is at rest, just like James asked, the fluid is at rest, that somehow means that all the forces that are acting, the net forces at play, must somehow be balanced, right? Because if there were a net force, there would be some kind of acceleration somewhere. So you can immediately conclude that if the fluid is at rest, the net force at any given point of the fluid would be zero. So in this case, for example, we know that there is a pressure here, and the force would be coming this way, and actually the area vector would be, also involved and so on. But the fact is that for the fluid to be at rest, the force at every wall that you will feel must actually be perpendicular to the surface here. And the reason is, if it were not, if there were an unbalanced, suppose there was an unbalanced force here, that unbalanced force would stimulate the fluid to actually move here, and then the condition for the fluid being at rest would be violated. So for the fluid to be at rest, it is therefore imperative that the force that is being exerted by the liquid on the walls be exactly perpendicular and nothing else. So this is the condition, by the way, that you will reach eventually, that all the forces that will be stabilized as the fluid ceases to move would be pressing perpendicularly on the wall in such a way that it doesn't move. And that again happens very quickly, because sound carries this energy at about, in this case it's more than 300 meters per second. Sound will travel faster in a denser medium. Okay, any questions? Alright. So now let's go to the consequences of Pascal's principle. So let's go to the car jack I was telling you about, hydraulic jack. The hydraulic jack, if I make a cartoon of it, would look something like this. Let's say this is grossly exaggerated, so don't even try to scale anything as reasonable. And let's say there is a surface here, and let's say your car is here. Let's make it a fancy looking car. It's broken down. So the car is there, and your foot is here. So as I said, it's not to scale. So your foot is here, and you are pressing on it. So you're applying a force this way, and hence you are giving it a certain amount of pressure. That pressure ends up being transmitted on the other side, because the fluid, let's say, is at rest. When you have applied the pressure, you are able to basically see that the pressure is approximately same everywhere. So suppose this area here is A1, and the force you have applied downward is F1, and suppose the area here is A2, and the force that this guy applies on the surface and the surface applies back on this guy is some force F2. Then by Pascal's principle, so Pascal's principle tells me that the pressure here, which would be F1 over A1, must be equal to the pressure at the other side, which is F2 over A2. Or I should be able to write A2 over A1 is equal to F2 over F1. So by adjusting the areas, I should be able to apply effectively a much larger force on the other side. Now how weird is that? Now there is nothing weird about it at the end of the day, because the amount of energy that you will give to the fluid by pressing it, energy cannot be created or destroyed. So that energy will be transmitted on the other side. So in other words, you can press it by a foot, but the car will not go up by a foot. The car may go up by a millimeter. That's the price you're paying. You're going to pump it many times to be able to get the car up. And that's exactly the way it works. So the point that therefore would be that you can easily generate 100 times more pressure. So if A2 is, let's say, 100 A1, right, then that would imply that F2 is also 100 F1. So F2 is going to be 100 times larger as well. So if F2 is 100 times larger, then there is no problem. Then you are generating certainly enough force to lift the car. But the fluid volume, the fluids are mostly incompressible. You won't be able to compress water easily. Gases may be compressible, but liquids, by fluids I here mean liquids. So let's say fluids. Instead of writing fluids, let me just be more specific and write liquids. Air can be quite compressible. A gas can be quite compressible. So let's say liquids are mostly incompressible, which would mean that if I depress this by some distance d1, then the volume of the fluid I'll be pushing down would be A1 d1, and if this is A2, then A1 d1 by the incompressibility argument must be A2 d2. So d2 then would be A1 over A2 times d1. So as you can see, it's A1 over A2, the inverse of A2 over A1, that controls by how much the car will rise. And of course, since energy is conserved, you also have the relationship that F1 times d1, which is the work done on the left side, is also equal to F2 times d2. It's a relatively simple physical problem. I can give you simple exercises on this in the exam and so on, because the exam is supposed to be comprehensive. I have to invent little things, but these are the kind of things that I'm trying to make sure that you guys can do. Okay? Questions? So this stuff is pretty easy, but now we'll get into stuff that's not necessarily all that easy. Suppose I consider a fluid whose density can somehow change, but we have to be a little careful. What I want to do really is talk about pressure dependence as a function of depth and density. So the easiest way to relate to this problem is, for example, you know that when you take a flight, the cabin is pressurized, right? Otherwise we'll all die. The cabin is pressurized in such a way that the air density in the cabin is something that we are comfortable to. If the air density is too little, then we would have great difficulty breathing, for example. People's sensitivities vary to air density. I am pretty sensitive, maybe because I used to be a smoker a long time ago, but for example, every time I go to, let's say, Colorado mountains or the mountains of New Mexico, these are places I go to often because I enjoy being there, it takes me about 3 to 4 days to get acclimatized. For most people, that's not needed, but for me it is. The same thing is also true for one of my children who is perfectly normal and athletic, but she cannot handle traveling to very large heights without proper acclimatization. She has breathing difficulty, and I have the exact same problem. Why is that? Because the air density goes down. If the air density goes down, oxygenation goes down, and hence the oxygenation that you are used to for breathing is not there. It's much less, and your body takes a long time to adjust to it. So that's basically what it is. So, at any rate, if you took a flight to Albuquerque or Boulder, you shouldn't get off the plane and start running, even if your lungs are in great shape, because you'll be panting in no time. The oxygenation is much less. These areas are about a mile higher than Buffalo. So a mile higher would mean about 7,000 feet. That said, I have no difficulty if I drive up to 12,000 feet, 13,000 feet, 14,000 feet. I've done that many times. I have no difficulty if I drive up because that's a much slower journey. Anyway, air density is very important is what I'm trying to say. So let us set up something that allows us to study pressure change as a function of height. Pressure change as a function of height. Okay? So the way the arguments begin are very simple. So in this case, we are talking about, let's say, for example, air. We are not talking really about a dense fluid. We are talking about air. Air, of course, is a composite gas. Air is made of nitrogen, oxygen, hydrogen, etc., etc., etc. So air is a pretty complex quantity, but we think of air as some kind of a simple gas for now. So let's say we take an imaginary slab of air. It doesn't exist. We just imagine there is a slab of air. Let's say the cross section here is A, and let's say this is the height delta y. Okay. So you can think of this, therefore, this level as y, this level as y plus delta y. Okay. So in other words, we are assuming that it's upward y, that is the positive direction of y. Okay. And we can now estimate, let's say the density of air in this slab is rho, but since density can change with height, I would call it rho sub y. So at this point, I should be able to write the mass of this slab, of this imaginary slab of air. Let me go here. I can think of it as a small mass, delta m, and delta m mass is volume times density. So the volume would be the cross-sectional area A times the thickness, so delta y. So this would be the volume times density, which is rho y. That would be my density. So we know that density is mass is volume times density, so that's exactly what I'm doing. Okay. So now let's look at the same thing here and look at a force diagram, free body diagram of what are the forces at play. And I would imagine that there is some force from above because there is always an atmospheric pressure. Atmospheric pressure is in all directions, so presumably there is a force from below, so let's call that F1. And this has a certain mass, so therefore there is a delta m times g downward at play. So if I look at the free body diagram, then it would look something like that. Okay, very simple argument, but it's not so simple that you can take it lightly. So I should be able to write a force law. The upward force is F1, the downward force is F2, so I would put a minus sign, and there is another downward force which is minus delta m times g, and since this imaginary slab of air is at rest, that must be 0. So I should be able to then do a bit of calculation. I can write F1 as the pressure at y times the cross-sectional area A, because pressure times area is force, minus pressure at y plus delta y. See, now the height dependence is coming in, times A, right? Minus delta mg. I found an expression for delta mg, so that will be A delta y times rho y times g is equal to 0. So the force equation that I wrote, based upon balancing out the forces, just to make sure that my slab is in equilibrium, begins to look like that. Which is very nice, because I can actually cancel out the cross-sectional area A, because that is no longer important. So I would have P y plus delta y, or let's write it like this: Py minus P y plus delta y divided by delta y must be equal to then rho y times g. But the way of writing this is actually a little different. Instead of writing Py minus Py plus delta y, one writes Py plus delta y, which is the pressure above, minus Py, which is the pressure below, divided by the distance involved between the measurement of the two pressures is negative of rho y times g. Okay, so this is what we measure when we measure hydrostatic pressure. Actually, when the weatherman or the weather woman gives you the weather and gives you a reading of the mercury, this is the pressure they are talking about. The pressure of 76 centimeters of mercury is the pressure involved. Okay, so this is a very important equation, because this equation has a critically important message for us, and the message is that as we go up, gravity being pointing down, you can see gravity is involved in our arguments here. As we go up, gravity pointing down, the pressure of the air is falling, which is exactly something that we know, which is why, as I said, when I go to Colorado, or when I go to New Mexico, or when I go up to the mountains in the Himalayas, for example, I have trouble breathing. A little bit of trouble, not a great deal of trouble, but then again, I don't go to 20,000 feet. So, and that's natural, because the pressure falls. If the pressure falls, the oxygen content is also going to go down, and therefore my blood will get less of a supply of oxygen than what I'm used to, and somehow I'm more sensitive to that than many people. All right. So, any questions on that calculation that I did? Go over it very carefully, because that calculation is critical to understanding properties of fluids. You have quite a few fairly complex things to do as far as the fluid is concerned. Okay, so this statement, as opposed to Pascal's principle, this is often written as Pascal's law. Okay, just so that you know. So if I say Pascal's law, that is what I'm meaning. All right, so be sure about it. So in general, then I should be able to write something like P2 minus P1, P2 being higher and P1 being lower, as minus rho g y2 minus y1. Again, all this is vertical because gravity is vertical, where in the picture I have this is y2 and the pressure here is P2, and this is y1 and the pressure here is P1. And density is approximately constant. And G is, so Y is up and G is down. This is the picture. So the way I have derived that over there in the box, I have kept density rho as a function of y. That's why I put in a rho sub y. So if you know, for example, how density would change as you go at higher and higher elevations, you can put that into the equation and solve it, and it will give you a fair amount of detail as to how the pressure will fall. Here on the other hand, at the simplest level, we have kept the density to be approximately constant. So that restricts you to considering y2 minus y1, which is small, right? Because air density we know changes. Just a few things I want to mention. If I could take an air column, so this is, let's say, sea level, and this is, let's say, the top of the atmosphere, edge of space. Then we know that the air is dense here and less dense as we go up. Ultimately, the air pretty much thins out. In fact, we won't be able to breathe, no matter how good you are in terms of your lungs and athletic capacity. Once we get up past 30,000 feet, it's very difficult to breathe past 30,000 feet, even if you train yourself very well. 30, 35, beyond that, your body just can't get enough oxygen. But the edge of space is quite a bit of a distance up. The atmosphere is not very thick for Earth, but it's also not that thin. But once you get up to something like 120, 130, 150,000, you are literally almost out of enough oxygen density for most life to be possible. So, but just to give you a sense of numbers, the density of air here at the base is approximately 1.2 kilograms per meter cubed. Approximately. You can think of it as 1 kilogram per meter cubed. But that's how dense air is here. But what is really interesting is that the pressure that we feel here, pressure of course comes from all directions, but the pressure that so here you are, the pressure that's hitting on top of your head, that pressure is that's the pressure. It's 10 to the 5 newtons per meter squared. So when we talk about 1 atmospheric pressure, that's what we're talking about. This is the definition of 1 atmospheric pressure. So this is just on the surface of the earth. That's what our lungs are used to. Okay? So that's a tremendous amount of pressure if you think about it. So naturally our bodies are tuned up to really not feel that. And that's the reason why we are very comfortable at this level. And our bodies, get out of tune as that pressure begins to fall as we rise up, as per Pascal's principle. So how do we measure this pressure? The way you measure this pressure is actually quite simple. So if you want to see the atmospheric pressure, you can do a very simple experiment. So this is like seeing atmospheric pressure alright. So if I take a container, let's say with water or some fluid, some liquid, take a flexible pipe, preferably a transparent flexible pipe, and let's say we put the pipe in the liquid. So our pipe is sitting at the base of the liquid, rolled up like this. So the water has gone into the pipe, and now what you do is you take one end of this pipe and you close the end with your finger on the top tightly, and you slowly lift up this pipe, what you will find is the water will rise on the pipe as you raise the top of this pipe. So let's say this is how your pipe is, and this part is sitting in the water, and this is where your finger is closing the top of the pipe. You'll typically find that this water will rise up quite a bit. All kids like to play with their straws. I have not met a kid who is not interested in pulling all kinds of stuff out of some kind of a cup or something with their straws, right? Why? Because exactly of this capillary behavior, so the water rises. So what's really going on here? It turns out that the pressure here is the atmospheric pressure. All right? But since you have covered the top of this pipe with your finger, since it was down there, you are not really letting the atmospheric pressure affect the water level inside the pipe, because you have covered it tightly, as I said. And so the water continues to rise because the pressure here is lower than the pressure there. So ultimately the water rises to a point and stops, because now the pressure, let's call it P, I called it P2, I think. P2 is very small. How small can vary, but it's approximately 0. And here the pressure is P1. So you see, I should be able to make a statement writing P1 minus P2 is equal to the density of the fluid. In this case, the density of the fluid, let's say, is rho, and the height of the water column, let's say, is h. And of course we have g, so rho gh. This is Pascal's law. So I've done nothing but written Pascal's law for you. And if you do this experiment with various liquids, you will find that this water column height will change. Because clearly the atmospheric pressure is the same, but if the liquid is a light liquid, this will rise very high. But if the liquid is a heavy liquid, it will not rise as high. It turns out if you make something like this out of water, the height that you will get for the pressure to go to 0, roughly 0 at the top of the water column, will be about 10 meters, 30 feet, roughly. That's why we don't make water barometers. That's a barometer. We make barometers with mercury. Mercury is a very heavy metallic liquid at normal temperature. And for mercury, this H, so for mercury is denoted by Hg, this density, this height comes out to 76 centimeters. That's your 76 centimeters of mercury level at atmospheric pressure. So when the weather prediction happens, they would often say what is the pressure, and they would mention the pressure in terms of how many centimeters of mercury or millimeters of mercury. That's what they're talking about, because at normal conditions the amount of height rise you will get for a liquid of mercury, for a liquid like mercury, would be 76 centimeters. So in fact the density of mercury is quite heavy. Mercury is a metal, a very poisonous metal, and it's 13.6 thousand 10 to the 3 kilogram per meter cube. So you can see that water is much less. This is 13.6 kilogram per meter cube. Water would be 1000 kilogram per meter cube roughly, and H is 76 centimeters. So if you calculate from here, if you set P2 to be roughly equal to 0, then P1 by that formula would be the density of mercury, acceleration to gravity, and the height H of 76 centimeters or 0.76 meters. That's what 76 centimeter is. And that number comes out to roughly 1.03 times 10 to the 5 pascals or newtons per meter square. And that again is the atmospheric pressure that I just gave you. The atmospheric pressure is measured in that way because the atmosphere is pressing everywhere. But keep in mind, atmosphere is not only pressing from top to bottom. Atmosphere is also pressing here, 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 etc. The pressure is everywhere. So if I stick my hand out, there is pressure from here, there is pressure from here, there is pressure from here, pressure from here, and all the pressures are the same. Atmospheric pressure literally surrounds us everywhere. It's not like we are squished from top and expanding on the side. It's not like that. It's from every possible direction. All right, with that, let's go to the quiz.